Okay, welcome. So I hope everybody's still doing well. Um, just a reminder, we have a homework due today and another homework assignment, again, mostly computational, is already posted. It's just a problem from Cessna. So I wanted to finish up with this kind of classification of order parameters and their symmetries. And one of the most important applications of this whole idea is the classification of the defects that you can have in ordered phases. And so the standard example for that is what's called a dislocation in a crystal. Okay, the idea is quite simple. So for simplicity, let's consider a two-dimensional one because that's easier to draw. So we imagine that we have some kind of two-dimensional crystal. And so they're atoms, regular spaced. Okay, so this is, of course, what we sometimes call a perfect crystal. Every atom is exactly in the right place. And if you grow crystals very carefully, then indeed you can achieve an arrangement like that. But in practice, that's almost never the case. And loosely speaking, that's because crystals grow from some initial seeds. And in a typical melt, you will have more than one seed, and they start to grow independently. And of course, they don't initially know about one another. So typically, whenever these seeds eventually emerge, then there will be some kind of imperfection. So for example, the simplest kind of imperfection that you could imagine is that there was one crystal growing from the left, and then there was another crystal growing from the right. And when they meet in the middle, they don't quite fit together. Okay. So again, there's atoms over here, as the crystalline planes don't quite match up. Okay. Something like this. Okay. So, so one way we could try to look at this is that, say the crystalline plane here on the top is a continuation of this one. The crystalline plane on the bottom is some kind of continuation of that one. But then in the middle, there's some kind of imperfection where it doesn't quite work out. So there's some kind of ambiguity how I should connect the crystalline plane in the middle. Okay. So one simple observation about this is that these sorts of imperfections, you can think of them as being detected by loops that go around the imperfection. So if, for example, I draw a loop around this imperfection here, okay, so this is a regular loop in coordinate space. Then this loop detects the imperfection in the following sense. If I draw a similar loop away from the imperfection, say I draw one here, okay, then you see that away from the imperfection, the loop cuts through an even number of crystalline planes. So it goes to the one on the top. So if I highlight that briefly, it goes to here, it goes to here, it goes to here, it goes to there. So it cuts through an even number of times. Whereas the one that circles around the dislocation, that cuts an odd number of crystalline planes. Okay. So that's a simple observation. So the loop around the defect intersects an odd number of planes. Okay. And there's a very nice way to formalize this in terms of this mapping from real space to order parameter space that we've looked at, okay? So let me try draw the same picture again. So, so the critical place that we're looking at is this thing in the middle where I have a crystalline plane coming in and it kind of goes up. Then there's one in the middle that doesn't quite match up. Actually, now I'm drawing it backwards. Yeah, actually, I can still save this picture. So let's view it as a picture of this. Okay. Okay. So then this is the situation drawn above. Okay. So, and now I can look at it in terms of this order parameter that we studied. So what was the order parameter? The order parameter was a displacement vector relative to a perfect crystalline plane. And I mentioned that it doesn't really matter what we use as a reference plane. We can either use the one on the left or on the right. So of course, the direction in which they're displaced is the y direction. So you can view the crystal on the left as not being displaced at all. So these crystalline planes are exactly in the right spot. And if the crystalline spacing is A, then this plane here is displaced by plus A over 2, and this plane down here is displaced by minus A over 2, okay? And we're a little unsure as to what to do about the plane in the middle, and you'll see in a second why that is, okay? So I can now try to match this, these displacement vectors, as we mentioned, the natural place where they live is they live on a torus. So let me try to draw that torus. Okay, why was that a torus? That was because the displacement vectors, they varied between 0 and A. But once you get to A, you're of course back to the perfect crystalline ordering. And that's exactly what a torus does, because if you go once around a torus in either this direction okay, or that direction, then you come back to yourself, okay? So let's now analyze the situation that we have if you make a loop around this location. So imagine that you travel along this kind of path here, where we're going around to this location. Then where do we start? Well, we start with the displacement vector that's 0. So we start somewhere here. But as we travel along, we get to this point down here where now the displacement is minus A over 2. So we somehow traveled in the negative y direction until we get to minus A over 2, okay? Going the other way, going backwards, we eventually get to this point, which is the displacement of plus A over 2. So we're traveling in the other direction, and we eventually get to plus A over 2. But by periodicity, plus A over 2 and minus A over 2 are the same thing. So if I follow this loop, I go all the way around this torus. So a loop in coordinate space that goes around at this location is a loop in order parameter space that goes once around the torus. So this here is order parameter space. So let me try to draw this one more time. Okay. So again, the situation I drew on the left was some kind of dislocation. Oops, a little bit messier. Okay, and then on the right, I had order parameter space. So again, you can imagine two kinds of loops. You can imagine the kind of loop that I just drew that goes around the dislocation. That's a loop that goes around the torus like that. Or you can imagine another loop that doesn't cut through the dislocation. So you could imagine a loop over here. Okay. So a loop like that, that just never, you know, the displacement vector never changes. In that regime, for example, the displacement vector is always 0. Or you could have drawn a loop over there, something like this. In that case, the displacement vector is always minus a over 2. So these are loops that don't really go anywhere. That's a loop that just circles around here. And the other one is a loop that circles around here. Okay. So you can see that what a dislocation is some kind of loop in order parameter space that goes at least once around the entire loop, that goes around once the torus. So, so we conclude from that that defects are somehow detected by non-trivial loops. So what do I mean by non-trivial? It's a loop, the red loop has the property that it cannot be simply deformed because it runs around the torus. You cannot smoothly deform it to a trivial loop that doesn't go anywhere. So non-trivial means cannot be deformed. So a non-trivial loop is just a little loop that you can shrink to a point. Okay. So, so if you make it even more abstract, then again, real space after all was just ordinary two-dimensional plane. So that's where the lattice lives. And then we had this map. The order parameter was a map. Xi of x was a map into order parameter space, which was a torus. Okay. And so the thing we discovered is that dislocations or defects in this crystal are detected by loops that go around them. So there's a loop and it goes around this defect. Okay. And it's a defect provided the loop is somehow non-trivial. So the loop travels around the torus, either along this direction or along the other direction. Okay. So there's a fancy mathematical way of saying that somehow what you should consider if you want to study possible dislocations in crystal is you should somehow consider the kinds of loops you might encounter in order parameter space. So if you want to classify defects, then that's somewhat the same as the study of non-trivial loops in order parameter space. Okay. So what is the point of these kind of non-trivial loops? I mean, the observation is somehow what we mean by defect in a lattice is a thing that can somehow not just disappear. Okay. In this case, the reason it cannot simply disappear, if we go, actually, let me show you an example of something that can simply disappear. Maybe that makes it more obvious. Okay. So suppose we have the same situation that we had before. Okay. But now it actually just returns on the other side. Okay. And again, so there are atoms here. Okay. So this is the kind of defect we can hope to just slide out. So I can take the atoms in the middle and just slide them through the lattice and they can go away. So that, that effectively is some kind of defect and some kind of anti-defect, and that can just go away. But certain defects, real defects that are detected by these non-contractible loops, they cannot just go away for the same reason that this loop around the torus cannot be simply unbound, okay? So the usefulness of this whole theory is you can classify what kind of defects there are that cannot just disappear, that the only way to get rid of them is to slide them all the way to the edge of your system, okay? So, so what these non-contractible loops somehow detect are real defects that cannot just go away by a thermal fluctuation. So, so what we need to study are these non-trivial loops in order parameter space. And it turns out that there is a mathematical theory that's somehow designed to do precisely that, okay? And so this mathematical theory just has a name. So condensed matter theorists at some point discovered that this mathematical theory already existed. And so the mathematical theory was called homotopy theory, okay? And so this thing that we just discussed, which is what are equivalent contractible or non-contractible loops on our order parameter space, is detected by something called the first homotopy group. Okay, and that just has a name. It's called pi1. And somehow the question is, you take a given space like the torus that we have now, and you want to ask what kind of non-contractible loops are there. So the order parameter space in our case, that was a torus. And in the case of a torus and of loops, we have some intuition as to what the non-trivial loops are, because if I draw that torus, okay, so we know that certainly we can make a non-trivial loop by going around, okay? But we can, of course, go around more than once. So you could imagine, instead of going around once, you could go around twice. Okay. And so going around twice, you cannot smoothly deform that to going around once. But of course, you can go around once and then you can go around backwards. That should be the same as doing nothing at all. Okay. Or you can take, of course, you can make a loop in the other direction. So you can take this space. Okay. And now you can decide to go around the other direction. So a loop that goes around the other direction on this donut cannot be smoothly deformed to a loop that goes around the first direction. So somehow these loops are classified by two numbers, and these two numbers are somehow winding numbers. They tell you how many times you go around each one of the directions in the torus, okay? And the way mathematicians say that is that this homotopy group is just a product of two numbers that are integer numbers of either sign. Okay. So again, this object here is called the first homotopy group. Okay. This object here is our order parameter space. And these here is two winding numbers, which are two integers that are either positive or negative. Okay, so so number one, so if you wish, real space of course lives here. So this number one refers to the fact that we do one-dimensional loops. So the one just refers to the fact that we do simple loops, which is a one-dimensional object. And you'll see in a second that there are more complicated objects where the thing we do in real space is more than just a one-dimensional walk. Maybe we do something in 2 dimensions or in 3 dimensions, and then you need homotopy groups with higher indices like 2 or 3. So we'll see examples of that in a second. And so why is it a group? It's a group because you can take different loops in order parameter space and just compose them together. So if you have 2 loops that go around in the same direction, you can compose them, and then you have a loop that goes around twice. Or you can take one loop and then compose it with the loop that goes backwards, which is the equivalent of doing nothing at all. So it's a group because there's some kind of composition law, there's an inverse, and there's an identity. There's a notion of doing nothing at all. So there's pi1, oops. Where did it go? So this pi1 of T2 is a group because there's a kind of multiplication law for loops. And this multiplication has an identity and an inverse. Okay. And what is amusing is that, again, that's kind of relevant to physics because so this is a purely abstract kind of group where you multiply together loops. But of course, something like this can happen in a real crystal because you can have crystalline defects and you can ask yourself what happens when 2 of them meet. You somehow slide around the crystal, 2 of these defects meet. It could either be that they meet and they just annihilate each other, you're left with nothing. So that would mean in terms of this group multiplication that you had one defect with the positive winding number and it made another defect with the negative winding number, they met and they just annihilate into nothing. But it could also be that you have 2 defects and they both have positive winding numbers. They meet and then the defect can't go away. You must have some kind of higher order defect at the same point. And indeed, there are many, many complicated situations that people can study where, you know, many crystalline planes meet and it's not a priori obvious whether these defects can go away or they have to somehow stick together and form higher order defects. And that can be studied by this kind of classification. Okay. So instead of trying to draw more and more pictures of crystals, I can give you references where you can look at stuff like this. I'll maybe give you just a few more examples. So another important example is a superfluid. Okay, so what was the situation in a superfluid? So in a superfluid, we have some kind of 3-dimensional fluid. So real space is just Euclidean R3. And remember that order parameter space, in the case of a superfluid, there was the phase of a wave function. So in that case, order parameter space is not a true torus, it's just a one-dimensional circle. So order parameter space is a circle. Okay. And so then we have some kind of map. So that map was, we take a position in real space and it gets mapped onto a phase that lives along a circle. So this kind of arrangement, by the way, does not have point defects. This kind of arrangement has line defects, as we'll see in just a minute. So the line defect is called a vortex. So I can draw an object which is a one-dimensional defect called a vortex. How do you detect a defect that's one-dimensional in a three-dimensional world? It's actually still just a loop. So if you wanted to detect a point-like defect in 3 dimensions, we'll see that in a second. The way to detect that is a sphere. But a line-like defect in 3 dimensions, it's still detected by just a loop around it. So this thing is detected by loops that go around it. Okay, and so what happens when you travel around this kind of one-dimensional vortex-like defect? Well, obviously the idea is that the phase goes from 0 to 2 pi. Whereas if you have a so the wave function does indeed go back to itself, because giving a wave function a phase of 2 pi is the same as giving the wave function no phase at all. Okay, so you can go around a closed loop around a vortex. The phase changes from 0 to 2 pi, meaning the wave function is perfectly continuous. But you go around this non-trivial circle in order parameter space, which means that this kind of defect cannot just disappear. And in fact, the only way you can have a defect like this, if you make the loop closer and closer, see the wave function still has to wind all the way from 0 to 2 pi. So it means that at the defect itself, the wave function actually does have to vanish. Again, it's like one of these p-state wave functions where indeed the phase goes from 0 to 2 pi as you travel around. Okay, so this is a line-like vortex. So what is this thing classified by? Well, this thing is still classified by loops, so we detect it by doing a loop. So in the language of these homotopy groups, it is still pi1 because we're using loops. But order parameter space is now a circle. So it's pi1 of a circle. Okay. And again, intuitively, it's clear what that is. If you do loops around circles, it's just one winding number. So in the torus, we had 2 winding numbers. Here, there's just one, and that can be a positive or negative integer. So this is, again, this group of positive or negative integers. So in this case, again, defects are still detected by loops. Okay, order parameter space is a circle. Okay, and defects are classified by just one winding number. Okay, that can be a positive or negative number. So you can have something like a positive winding vortex and a negative winding vortex. And obviously there's a process where a positive winding vortex can meet a negative winding vortex and the two just annihilate. But if 2 positive winding vortices meet one another, then you must somehow get a double vortex that has twice the circulation strengths. Okay. Final example that I wanted to give. Yeah, that's it's supposed to be this kind of standard math notation, you know. So the real numbers are oops. So this is the real numbers, and these are the positive or negative integers. I'm not drawing this well. So R is the reals, and Z is the integers, positive or negative. So, okay, final example is a magnet. Okay, again, going to consider a three-dimensional magnet. So real space is a three-dimensional thing. Okay, and order parameter space, we saw that if you have a Heisenberg kind of magnet where the magnetization is just a vector in real space, okay. So this is not an Ising magnet, because in an Ising magnet, the order parameter is either up or down. So this is again, sometimes called a Heisenberg magnet. Magnetization is a three-dimensional vector. And in the magnetized phase, the length of that vector is somehow fixed at something, the magnetization of the system, but the direction is not fixed. So the order parameter lives on the surface of a three-dimensional sphere. Okay, so a two-sphere. So, and this is my mapping. So my mapping is, okay, the magnetization as a function of x. Okay. So again, it's maybe not a priori obvious what kind of defects I can have here. Maybe they're point-like defects, maybe they're line-like defects. We'll eventually encounter wall-like defects. So this system turns out to have point-like defects, because you can have the following situation, that there is a point somewhere in the system. Okay, so here's my defect. And the defect is surrounded by a magnetization that's just pointing radially outward. In all three directions. Okay. So all of these magnetization vectors, they all have the same length. So they all live on the order parameter sphere, but they're pointing in different directions. Okay. So this point-like defect, that you cannot detect by a loop. And that's sort of intuitively obvious, because if I try to draw, I mean, in the previous example, the superfluid, if you draw a loop around this line, then you can try to slide the loop up or down, but it always surrounds the line. Whereas if you have a point, of course, you can always slide the loop past that point and then contract it to nothing. So the way you detect a point-like defect in three dimensions is you have to surround it by a sphere. Okay. So this thing is detected by a sphere in real space. Okay. And what happens now is that if you sit at the north pole of this sphere, you see the spins pointing up. So you sit, for example, here in order parameter space. But if you sit at the south pole of the space of the sphere in real space, you also sit at the south pole of the sphere in order parameter space. Whereas if you were in a regular magnetized phase, where all the spins are pointing in the same direction and you go around a sphere in real space, you always stay at the north pole in order parameter space. So the way you can describe that is, again, using this mathematical language, is that now we're not looking for equivalence classes of loops. We're looking for something that's somehow harder to visualize. The reason it's harder to visualize is, again, this kind of composition law for loops, I can sort of intuitively see how that works. So I have one loop that I traverse, and then I traverse another loop. But now I'm not traversing loops. Now I'm taking a path along a two-dimensional sphere, followed by another path along a two-dimensional sphere. I find that harder to visualize, but it's in the end exactly the same sort of operation. So in this case, what we have to consider is not equivalence classes of loops, but equivalence classes of maps from two spheres, okay? And so this is equivalence classes of maps from two spheres on two spheres, because order parameter was another two sphere, okay? So this one, again, is maybe less obvious exactly. So we again imagine that there is a kind of winding number here, because if I take the regular magnet with all the magnetization vectors pointing up, so then I always stay at the North Pole. So that's the analog of the sort of trivial loop that immediately loops back to itself. But around this point-like defect that I just drew, again, if I go around the sphere, I cover the order parameter sphere exactly once. And that's a similar situation where I cannot go back to the situation where I just stay at the North Pole, because I somehow have to cut and slice it open and then contract. And so that's similar to cutting the loop. So this map is also non-trivial, and it's again classified by some kind of winding number. And you can convince yourself that indeed there are maps. So the one that I drew previously, where the North Pole is mapped to the North Pole and the South Pole is mapped to the South Pole, that has winding number one. But you could imagine constructing maps where you wind more than once as you go from the North Pole to the South Pole in real space, that you go from North Pole to South Pole more than once. So higher order parameters, higher winding numbers are also possible, okay? So again, this object here, this is now called the second homotopy group. Okay, this here was order parameter space. And this here is yet another winding number. Okay. So this kind of configuration that we just encountered, it's a funny defect that can occur in magnets. So again, we had this defect, and it was surrounded by a magnetization that just points radially outward. Okay, so that kind of defect has a name, sometimes called a skyrmion. Okay, or also sometimes called a hedgehog. You know, I suppose you're supposed to visualize a little hedgehog that you know, is all curled up and all the spikes are kind of pointing out. Okay, so that is indeed a kind of defect that you can go look for in actual magnets, and it has indeed been discovered. And you have a similar situation where you can have positive winding number skyrmions and negative winding skyrmions, and they can somehow come together and annihilate, and you can have two skyrmions and they come together and they form a higher order one. Okay. So, so these funny homotopy groups, by the way, so the very simple ones, like what is a loop on a circle, they're sufficiently easy to visualize that you can immediately kind of identify how many winding numbers there are, what kind of winding numbers occur. There are more complicated situations where it's really just far from obvious. And computing these homotopy groups is actually somewhat advanced mathematics. So what physicists simply do is that there are many, many review articles or textbooks, and somewhere in the appendix, they simply have lists. So there are all sorts of possible order parameter spaces, you know, circles, spheres, tori, various other groups, you know, groups of orthogonal rotations, God knows what, it's just a long list. And they just give you tables of what these homotopy groups are. So simply, when you have some kind of material and you've identified what real space is and what order parameter space is, then you can just ask yourself what kind of defects might occur. Could there be in a three-dimensional system, if you suspect that maybe they're point-like defects, then you have to look at the second group. If you suspect that maybe they're line-like defects, then you have to look at the first group. And then you just look up this table, whether this first or second homotopy group of your order parameter space, whether that's not trivial, whether that's classified by certain winding numbers, and how many there are. And so after looking at that list, you just know what kind of defects occur in your system. Okay, so you cannot compute what the energy are or what the, or how likely they are to occur, but you can determine whether stable defects do exist. Okay, so that's important knowledge about many systems that have broken symmetries after you've gone through a phase transition. Okay, so so that's the general idea. Again, there's some more examples in the book, and I encourage you to take a look at that. But I was gonna end the discussion here and go on to another subject. So, so if there aren't any more questions, I'll continue with something slightly different. Okay, so so this subject is something that the book actually hides, I think, in a problem, even though it's kind of an important subject, which is, so everything so far has in some sense not really been quantitative. I mean, we've somehow classified what kind of phase transitions occur, what kind of order parameters there are, what kind of symmetries exist, what kind of defects there are, and again, what kind of stable defects there are, but we haven't really computed anything about them. So the question is whether one can construct some more quantitative theories. And a full quantitative theory of phase transitions is kind of a complicated subject, but there is a simple theory that's often quite useful, and that's called the Landau theory of phase transitions. Okay. So this theory is not actually exact. Okay. It's a kind of theory that's sometimes called a mean field theory. But even though it's not exact, it's often actually quite accurate. And even in cases where it's not exact, it actually ends up being the kind of starting point for a more exact treatment. Okay. So what is the idea? Some of the idea is that we're interested in, we have a substance that has some kind of order parameter, like a magnetization, say, and we're somehow interested in, what kind of magnetic configurations do actually occur at some, temperature T. Okay, so so the idea is to take this order parameter, and again, the order parameter is already some kind of macroscopic variable. We somehow imagined that we took the microscopic spins, we averaged them over some neighborhood, and now we have a kind of local magnetization. And so the idea is to take that order parameter and now treat it as if it were a thermodynamic variable, as if it were something like an ordinary density, okay? So the idea is we treat the order parameter as a thermodynamic variable. That's sort of idea number one. The second idea is we're going to do that in the vicinity of the phase transition. That's somehow actually the most interesting regime. And so in general, just to say that there's a thermodynamic variable really doesn't do all that much for you. It just means that, you know, thermodynamic quantities like pressures and free energy densities and so on are now functions of that thermodynamic variable. But if I don't know anything about that function, then I haven't really made that much progress. And so what I will assume is that I'm in the vicinity of the phase transition so that the magnitude of that order parameter is somehow in some sense small. So I assume that near phase transition, the order parameter is somehow small in some suitable sense. We still have to answer at some point small compared to what, but we'll get to that. And the way we will use that is that we will assume that other thermodynamic variables, like say free energy, can somehow expand it as a Taylor series. Okay. So what does that look like? Well, again, if you just do it for the free energy itself, so we have some kind of free energy that we call A. A was a three-dimensional integral over a free energy density. Again, most books call free energy F from the start. Our textbook calls the free energy A, but then the free energy density is indeed called somehow script F, okay? And so what I will now assume is that this script F is a Taylor expansion in the order parameter, okay? And here for definiteness, I will indeed consider the Ising model. So we'll consider Ising. Okay. Then there's some order parameter, which is not a vector, but just an ordinary number. But the system is symmetric in plus or minus m. So whatever Taylor series I'm about to write down, in the absence of an external field, only has even terms. So it has a term like alpha m squared, and the term is beta m to the 4, and in principle, many, many other terms. Again, the free energy in the absence of a magnetic field is even in m, but if you couple it to an external field, then there will be terms that are odd. In particular, the coupling to the field itself is indeed just h times m. Okay, so this is the external field. And since this m is a coarse-grained variable, which is a function of, you know, ordinary real space, in general, m is a function of x. And so we will therefore, in general, allow this free energy density to have gradients of the magnetization, okay? Which I think is something we actually encountered before when we looked at, I have to go back and look, when we looked at free energy densities as a function of the density. So in general, there can be a term that has gradients, and that term is usually called kappa divided by 2 times the gradient of m squared. Where again, in principle, there can be many more terms with higher powers of m or more and more gradients. So, but this expression here, that's the one that's usually called the Landau free energy. Okay. So this simplifies things greatly. There's still an issue, which is that, so this alpha, beta, and kappa, so on. So these are somehow constants, but they're still constants that depend on other thermodynamic variables. So the magnetization, the dependence of the free energy on magnetization is different at high temperature than at low temperature. So this means these alpha, beta, and kappa, I have to assume that these are actually functions of temperature. So this alpha is actually a function of temperature, okay? And again, that one too, I will assume, just like I assumed that the free energy was somehow a smooth function of the magnetization, I will assume that these coefficients are smooth functions of the temperature. And since from the start, I made an assumption that I'm somehow close to the phase transition temperature, I can expand, I can again just Taylor expand around the critical temperature, okay? So this is some kind of A naught plus A times T minus TC plus and so on. And similarly for beta, so beta is really a function of T, which is some B plus, what you call this, B naught. And so on, okay. So, so as we'll see in a second, for this theory to actually describe a phase transition, A naught must actually be 0. Okay, so this alpha is actually A times T minus TC, okay? Whereas the beta actually does start with a constant. So this beta, this is plus higher order terms. So this beta actually does start with a constant plus higher order terms. Okay. So, so how do I see that this theory does indeed potentially describe a phase transition? Well, if you are in thermal equilibrium, we saw earlier that if you have some kind of free energy density that depends on some variable in your system, then you find the correct ground state or you find the correct equilibrium state by minimizing free energy. And we went at some point through various ways of seeing that. So one way to see that was we saw that in the grand canonical ensemble, e to the minus f is actually the appropriate Boltzmann factor for some configuration, so that the most likely configuration was the one with the biggest Boltzmann factor, which is the one with the lowest free energy. We also saw that in a general non-equilibrium state, you will continue to produce entropy until you get to a state which has the minimum free energy, and then the system can settle down in equilibrium. So if you go back a little bit earlier to what we did in the semester, we went through this idea that you should minimize free energy. So here we have a free energy functional, which depends on the magnetization. So if you want to know what is the correct magnetization at a given temperature, what you should do is minimize free energy. Okay, so in equilibrium, we minimize free energy. Okay. So the contribution to the free energy that came from gradients of m was gradient of m squared. So there was a contribution that was gradient of m squared. So that one's always positive. So the best you can get is you can get that term to be 0, cannot be negative. And so the lowest free energy configuration is always one where the magnetization is just a constant. Okay, that's maybe not so surprising, provided that kappa is 0. So if kappa is greater or equal to 0. Okay. So once we decided that the free energy is minimized by the magnetization being a constant, we can try to determine what that constant actually is. Okay? And so that we just do by minimizing free energy with respect to m, or since at h equal to 0 is just a function of m squared, minimized with respect to m squared. And so, the function was just alpha m squared plus beta m to the 4. So if I take that derivative, I get alpha plus 2 beta m squared. And alpha we decided was, well, okay, actually, let me stop here. And so this we just set to 0. Okay, so that's how we minimize. And now I can, of course, just solve for m squared. So I conclude that m squared is minus alpha over 2 beta. Okay. So, so what does that mean? Okay. So m squared is minus alpha over 2 beta. Again, alpha was a times t minus tc. So I can write this as a times tc minus t. And beta just started out being a constant. And I think I now got the constant 2b naught. Okay. So what is happening here is we have a function that's alpha m squared plus beta m to the 4. So if I were to plot that function, so this is the free energy density as a function of m, okay? So it has two terms, alpha m squared plus beta m to the 4. So for the free energy to actually have a minimum, the quartic term must be positive. Otherwise, the whole free energy would be unbounded from below, and the magnetization would try to run off to infinity. So if this is a thermodynamically stable system, we assume that this is not the case. So we assume that beta naught is always greater than 0. Then if alpha is a times t minus tc, that means that alpha changes sign at the phase transition, so that above the phase transition it has a positive sign, and below the phase transition has a negative sign. So what this would look like is that for t greater than tc, both alpha and beta are positive. Okay, so then I have some kind of function like this. So this is t bigger than tc. And below tc, okay, now the alpha term is negative because it goes as a times t minus tc, so it changes sign. So the alpha term is negative, but the beta term is still positive. So the curvature at the origin is initially negative, but then the fourth order term takes over and curves it back up. Okay, so this is t less than tc. Okay, so this means that below tc there are two minima, here and here, and above tc there's just one minimum here in the middle. Okay, and now you see that why it is that we needed this alpha to have a vanishing constant, because we want the alpha to change sign exactly at the phase transition, so that we change from this one behavior where the minimum is always at the origin to the other behavior where the minimum is at some non-zero magnetization. Okay. And since we solved for a minimum in terms of m squared, there are indeed two minima, and the two minima are simply m is plus or minus square root of a over 2b naught times tc minus t. Okay, so far it's maybe not entirely obvious that this whole theory somehow actually predicts something, because we just simply constructed some kind of model that actually does have a phase transition. That's already a start. I mean, so here's some simple model where you actually will get some kind of discontinuity, that the free energy for a certain range of temperatures is initially always minimized by m exactly 0. And then below that temperature, it's now minimized by a non-zero m. But you actually get a little bit more, because what you get, for example, is now you can try to plot what, say, the magnetization actually looks like as a function of m, as a function of t, okay? Because we have an actual prediction now for the temperature dependence. According to this, the temperature dependence is a square root. Okay, so this behavior here is that the magnetization goes as the square root of Tc minus T. Where strictly speaking, we should keep in mind that this whole theory was constructed to be valid near the phase transition. So what the theory really predicts is that somehow, if you stay sufficiently close to the phase transition, you should get this kind of square root behavior. Okay, that's what the theory predicts. So this kind of prediction, by the way, is called a critical exponent. So what the theory somehow predicts, so again, it predicts that the absolute magnitude of m goes as the absolute magnitude of t minus Tc, oops, okay, to the 1/2. And as I say, in the lingo of phase transitions, this 1/2 is called a critical exponent. Okay. The reason that this critical exponent is somehow interesting, so this Landau kind of theory, for example, it obviously doesn't predict what these A's and B's actually are. They're somehow constants that you would have to measure in an experiment. But the square root behavior, that's somehow more general. That doesn't depend on the parameters of the theory. That only depended on this kind of assumption that everything was smooth so that it could be Taylor expanded. And it depended on this assumption that the free energy itself was even in m, so that only terms like m squared and m to the 4 occur, that only the coupling to h can give you terms that are odd in m. So the 1/2 is somehow a more solid prediction than the coefficients in front. And in particular, it's somehow independent of what precisely the system is. So any system that has an Ising-like Landau functional, so one that's just alpha m squared plus beta m to the 4, they would all have that critical exponent, which is 1/2. But the term, you know, the coefficient in front and the actual Tc and so on, that could, of course, be different. Okay, so that was somehow Landau's beautiful idea, that he could predict. He couldn't exactly predict where Tc is, and he couldn't predict the exact magnitude of the order parameter in the Tc, but he could predict the shape of the curve. Okay. Now, sadly, this prediction is not actually right. So this number can be measured. Again, you can take an actual magnet, or you can take the little Metropolis algorithm that you know wrote and try to study that very carefully. In this Metropolis algorithm thing, this, by the way, that somehow already turns into more complicated numerics, because again, any actual simulation has to be run for a finite number of spins and for a finite external magnetic field. And then you have to carefully extrapolate to infinitely many spins and 0 external field, and to read precisely the shape in this extrapolation, actually not that trivial, but okay, there are many algorithms that try to do that better. And now there's very accurate numerical data for actual Ising spins. Okay, so the correct answer So the correct answer actually does end up depending on how many spatial dimensions your Ising model lives in. So the Landau theory would not seem to depend on that, because the only thing we've used is that the form is alpha m squared plus beta m to the 4. It didn't matter that the real free energy was a 2D integral or a 3D integral or God knows what over that free energy density. Only the form of the density that mattered. But in the real world, it does matter how many dimensions your system lives in. So you can look at this in different numbers of dimensions. And this particular critical exponent, by the way, is usually called beta. Okay. So if on Wikipedia you look up critical exponents, this one's called beta. Okay. So the critical exponent is beta. Okay, and then you can make a little table. So this can be studied for a two-dimensional magnet, which is what we studied numerically, can be studied in 3 dimensions, which is kind of where a real-world magnet would live. And at least numerically, nobody prevents you from studying it in more than 3 spatial dimensions. So for example, you could look at 4. Okay. And so the numbers you find is in 2 dimensions, it turns out to be exactly 1/8. So that's because in 2 dimensions, as I mentioned earlier, the Ising model can actually be solved analytically. So there's an analytical answer ends up being not 1/2, but 1/8. Now in 3 dimensions, it's already a little bit bigger. It's 0.326, many more digits, okay? And in 4 dimensions, it actually is 1/2. Okay, that's sadly not the real world. So in 4 dimensions, the Landau theory is actually exact. And if you go to fewer dimensions, then it's only an approximate theory. And in general, again, in this Landau theory, all these critical exponents are always things like 1/2 or 1/3 or 2/3 or something like this. But in the real world, frequently, they're really just irrational numbers, infinitely many digits. So, so in 4 dimensions, the Landau theory actually turns out to be exact. And again, there's a fancy way to say this, which is people say that 4 is the upper critical dimension. So the upper critical dimension is if there ever is a dimensionality where the Landau theory suddenly becomes exact, or where mean field theory suddenly exact, that's called the upper critical dimension. So for the Ising model, that ends up being 4. Okay. So you can, by the way, now continue and compute some other stuff just to see that the Landau theory actually does predict things. Again, remember that the free energy density itself was alpha m squared plus beta m to the 4. And so now near TC, after all, we now determined the actual m squared. So alpha was a times t minus tc, and m squared we now determined to be a over 2b times t minus tc. Okay. And beta, again, beta we just approximated by a constant, which we call b naught. Okay. And m squared, of course, is now a over 2b naught t minus tc, everything squared. Okay. So you see that the 2 terms actually have the same structure. They're both proportional to a squared over b times t minus tc squared. One has a coefficient that's a quarter plus a quarter. The other one has a coefficient that's minus a half. So overall, they have a coefficient which is minus a quarter. So this is minus a quarter a squared over b naught times t minus tc squared. Okay. And this is really only the case. So we only get a non-trivial solution below TC. So this is the result for T less than TC. For T bigger than TC, the magnetization is just 0. And so the free energy is just 0. Okay. So now you can try to use thermodynamic identities to compute other things. So for example, the entropy density of the system is a derivative of the free energy density with respect to temperature. Okay, that's one of these thermodynamic identities. So I can just take this expression up there and just differentiate with respect to T. So what do I get? I get 1/2 a squared over b naught times T minus Tc. Okay, so what I learned from this is that near Tc, there's a term in the entropy density which is linear in temperature. That, again, is a prediction of the theory. And I can go one step further. If I differentiate that one more time, I get a specific heat. So the specific heat is proportional to T times ds by dt. So I differentiate that one more time. So this is T times a squared over 2b naught times 1. And since in this expression, everything after all was really expanded around Tc, to the accuracy of this theory, this is just Tc a squared over 2b naught. Okay, and this is for temperatures, again, this is in the regime where the free energy is non-trivial. So this result is the specific heat for T less than Tc. Okay, so what the theory somehow predicts is that in the specific heat below Tc, there is some kind of constant contribution which is absent above Tc. So this theory somehow predicts, okay, predicts some kind of discontinuity in the specific heat as a function of T. It predicts that there is something below Tc and nothing above Tc, that there is some finite jump. Okay. And again, you can compare that to either actual experiment or numerical simulation. Okay. So this too, by the way, is called a critical exponent. So in this case, the critical exponent is usually defined as follows. There's a contribution to the specific heat, which goes as T minus Tc to the negative alpha. So it's defined in such a way that if alpha is positive, then there's a divergent contribution to the specific heat. If alpha is 0, there's a discontinuity in the specific heat. And if alpha is positive, if alpha is negative, there's a kind of cusp in the specific heat. Okay. So this too, again, has been computed numerically. So for different dimensions d, where again, you can look at 2, 3, and 4. So this alpha is indeed 0 in 2 dimensions. It's 0 in 4 dimensions. And in 3 dimensions, alpha equal to 0 is actually a reasonably good prediction, but not quite right. So in 3 dimensions, it's 0.11. Okay. These are maybe not the best zeros ever. Okay. So this is a similar situation where in 4 dimensions, and in this case, actually also in 2 dimensions, the Landau theory is exact. Okay, but here it's only approximately true. Okay, although 0.1 is pretty close to 0. In fact, the fact that it's not 0 is experimentally kind of hard to see. Okay, so this Landau theory, again, in general, not an exact calculation, but it's at least it does make non-trivial predictions. And these non-trivial predictions, if you don't know anything at all, they're a sort of natural first starting point. And indeed, the theory can be used for a variety of other things, and we'll see more examples of what the theory can be used for on Wednesday. So I'll do a few more calculations. I already posted that, so there's a calculation of how you compute. In an Ising magnet, you can have a kind of defect where, you know, on the left all the spins are up, on the right all the spins are down. So this is a kind of wall-like defect. And the Landau theory now allows you to compute the likelihood of seeing a defect like this in a thermal system. So it allows you to understand the domain size in a magnet, for example. So it makes very non-trivial predictions, even though these predictions are generally not exactly correct, but they're kind of a starting point, as I mentioned. Okie dokie. Can maybe stop the recording.